Hello, hello. Hello, world, I mean. I keep forgetting. Talking to a whole bunch of platforms right now. It's really cool. Gotta love technology. Hello, Twitch. Hello, LinkedIn. Hello, YouTube. Hello, Twitter. Happy to be here today. Joined by Nick, head of developer ecosystem. We're going to be doing a part 2 on Quivr. So we did a part 1 last week, James and I. It was just a brief little exchange where I wanted to send some polys over to James. So I had to create a transaction to do so. But in order to actually create that transaction, I needed to know where to send the polys. So James needed to create an address. So that kind of just got us a little bit of a brief overview of some of the stuff in like our Bramble SDK library that we have at the moment, and how we're using it. And this is all focused on Tetra, which is the next major release for Toppl's blockchain. The current release is Dion. Tetra is upcoming. Hopefully, over the course of the year, you'll hear more and more updates about it. Alrighty. So yeah, I just wanted to quickly show, what we hope to accomplish today. So I explained what we did last week, but this week we're going to be doing part 2, going a little bit more advanced here. So we've got a little scenario here where James, Nick, and I are roommates in this hypothetical made-up scenario. We're not actually roommates. We live in completely different states. Yeah, for now, just pretend. But we're roommates, and the utility bill is due for our apartment. And it's due this month, and it is currently June 30th, and it is due real soon. The bill is for 80 polys, or dollars. You can think of it like dollars if you want. Unfortunately, James is out of town, so we're in a bit of a predicament here. It's just Nick and I. We got to pay this bill. Luckily, the three of us, we share an account here. I put account in quotes. We're not actually an account model. We're UTXO models, so we don't technically have accounts, but just think of it like an account for now. Spending from this account, it requires permission from at least 2 of us 3. So we all share and own the account, and we can spend from the account as long as there are 2 of us to say so. And that's real handy for this particular situation where James is out of town, and he can't help us pay this bill. So Nick and I, we're going to take care of it. Don't worry, James. We got you covered this week. Alrighty, so I am going to stop sharing, and I'm going to pass over to Nick, where he's gonna, get us started on some of this stuff. Sorry, I shouldn't have hit that button. This is gonna interrupt you. Let me just share real quick, and then I'll unshare.
Gotcha.
Okay, there we go.
Cool. All right, beautiful. All right, we're gonna start with this nice blank screen here, so we can start adding things. So the first thing that we're gonna need to do is obviously I need a key. I need something to reference myself on the chain. So I'm going to create a key. So let's call it generate, and then I also want to save this key so that way I can use it later. So we're going to make this runnable. So we're going to import this IO app from Cat Effect. Just a simple runnable. So I can actually generate that key and save it to disk. And then we're going to pull in some utils from last time. All right. So right here, it is saying that I need to implement the run method from Cat Effect. Easy peasy. So this is where we're going to start adding this logic to generate this key. So what I want to do here is actually use a for comprehension to just walk through the steps, since it's all since the end result is just we're going to do some printing and then save that key, but it's all side effectful. So we're going to run through it and then exit. So the first thing we're going to do is we're going to use our key initializer, yes, to create a new key. And so we are going to use, well, it's not popping up, but we want to create a new, there we go, okay. A new ed25519 key, which is the type of key that we use primarily for most of our keys now, versus like SecP or something else on like Bitcoin or Ethereum. We use ed25519. It's a really nice, fast, easy key to use. So I just pulled in this implicit up here to that's going to bring in some utility functions for actually generating this key. So I'm just creating a random key, not passing any like seeds or parameters or anything like that. Just create a simple one, and then we're just going to grab that secret key using pure. That's in the SK.
Yeah, hey Nick, just a suggestion. In the cheat sheet that you're not referencing, you may want to like copy paste all of the imports in ahead of time.
Fair enough.
It'll make it a lot easier. Yep.
Yes, because there's going to be some implicits and stuff like that. That's going to be fun. So yeah, I'll go ahead and just, there we go. All right, so yeah, so it's going to grab a lot of those instances and implicits and pull all those in. So that way everything will actually show up properly. That's fine. Let's see. Yep, so there. Now we can get our pure function. So now we're going to grab the verification key from that secret key. Let's see. Give it a second. Seal. Here. Let's give it a second and see if it's gonna. It might be because I'm streaming. It's gonna be a little slow on analyzing. Yeah. Ooh boy! Look at that progress bar. Cool. Gotcha. Okay. All right. So we'll grab that. I don't know. We're gonna assign this to this. There we go. Okay. And then, so from this verification key, we're going to get a proposition. So we're going to use a handy dandy type class that we have for this called .as proposition. So I'll actually take that verification key, the raw verification key, turn it into a proposition. So a type of proof that we're going to use to verify on chain, so using the public-private key pair that we just generated, this proposition is like an extra step for generating a specific proof to use on a network. So the actual lock on a box. So then from this proposition, we're going to create a spinning address. This is a nice thing about Scala, that we can have all these functions defined for us as these type classes ahead of time. So we're going to take the, what is it? Okay. Go ahead and do that. So this is going to be right, IO, returning a unit. So hopefully that will make all the squiggly lines disappear and make it happy. So we're going to take that spinning address. So now we have our proposition and our spinning address. So these are two of the main things that we're going to use on chain to create transactions and verify them. So the spinning address is the publicly addressable unique identifier. So that's going to represent me essentially. And then the proposition is the actual proof itself. So the spinning address is generated from the proposition. But the address is network specific. So it is checked. So when I generate the spinning address, it is particular to the the actual network that I'm using it on. In this case, a private test net. But and in this case, it's a mocked example. But the idea is that this spending address, I couldn't use the same address if I use it on the main net, like ToppleNet, or our testnet Valhalla. I couldn't take that same key from one of those and then use it like in a private testnet. But I could take the proposition, as far as I know. So we're going to go ahead and print both the proposition. So my proposition is, and then proposition. Cool. But this is not going to print out. This will print out the raw proposition. So we're going to go ahead and encode it. So we're going to grab the bytes of this. Okay. I can type that faster than it's going to pop up, apparently. So we're gonna grab the bytes from this, and then we're actually going to encode it as base 58. So all of our addresses and propositions, everything that we use in transactions, is generally encoded in base 58, which is the same as what Bitcoin has. It's a little bit easier to pass around than something like base 16 or hex for the most part. And then my spending address, GPP, and that is going to be the same thing. So I'm going to take my spending address, grab the bytes from it, and then encode that, not 2 bytes, to base 58. Cool. And then I think, let's see what else I got to do. And then, so the last thing we want to do, though, is actually save that. So I'm going to take my spinning address as a typed evidence. And then, so the last thing we're going to do is this. There you go, credential IO. Right. So we're actually going to take that typed evidence and we're going to write it. Let's see, to disk, so that way I can save it. So we're going to take our secret key, our typed evidence, our secret key. Wow, okay. Persistent bytes. And then we're going to encrypt it with this password. So it's going to create an encrypted file on disk that then I can go back and reference. So let's see. So it's going to put it in here. This is currently empty. So if I go ahead and run this, we should get a proposition and address printed out, and then have it pop up in that Quivr demo folder. Beautiful. Cool. So this is my proposition. So I'm going to go do some behind the scenes magic and pass it over to Sean. If I can find, whoa. Okay. Let's just change all the screens. All right, I'll go ahead and pass over to you, Sean. And then I guess I'll also pass this back. Control the screen.
Awesome. Thank you, Nick.
Cool.
Actually, before, well, never mind. We'll do it in a second. So yeah, I got the proposition from Nick here. So that is Nick's specific proposition. Doesn't include anything about James or myself. It's just for Nick, and it's just associated with Nick's verification key. Now, in an ideal world, he wouldn't have to send the proposition itself over to me because that reveals his verification key. He would instead send the spending address. But unfortunately, the mechanisms for what I'm about to show you, we can't currently support defining a threshold proposition out of only addresses. Anyway, let me go ahead and add my screen back in. So yeah, we're in part 2 here. Nick was kind enough to send over that proposition, that encoded byte string. So let me just enter that in real quick. Actually, no, I'm not going to do it there. Let me set up my for comprehension just like Nick did a moment ago. So set up a for, and then I'll yield nothing. Okay, and then so I'll get to Nick's proposition in a second. Forget about that. Let's start with we need my secret key. Okay, so I'm also going to participate in this exchange, so I need to load my secret key from disk. I already did that ahead of time, or I already created a secret key, so I'm just going to load it from disk. So my secret key, my name is Sean. I'm going to use this little helper method. If you watched the stream last time, this was really verbose. It took like 5 lines because you had to deal with error handling and whatnot. Which is good in a real world application, but it's bad when you're trying to demo something really quickly to, a live audience. So I created a little helper method here, low key, and it's just in this little utilities trait. And all it's doing is just taking base 58 encoded evidence and a password, and it goes and fetches a secret key from the credential IO, like from disk. Okay, so I'm going to load a key. So in this case, it's same as Nick. It's an ed25519 secret key. And I'm going to pass in the typed evidence of it and the password. Those are the 2 arguments that I need. I have these keys up here. I'm just going to copy from the cheat sheet that I don't have. Totally not using it. Okay, so Sean's secret key. I had a type annotation of that. So it's a secret key.ed25519. Cool. So that's just for me. Let's turn my secret key into a proposition. Okay, so Sean proposition, and this is just a proposition, is going to be Sean's secret key dot verification key, or VK, dot as proposition. It'll be slow for me too. We'll deal with it. Okay, so we have my proposition. That's one of the 3 things here. Remember, it's me, Nick, and James. James isn't here right now; he's out of town. So Nick and I have to cover it for today. But we do still need all 3 of our propositions. Okay, so James, before he went out of town, he was kind enough to send over his proposition. And so I'm going to copy paste that. So this is his base 58 encoded proposition. But again, I added a helper method because this was a nightmare in the last broadcast. So there's this little decode proposition that just takes this base 58 string, decodes the bytes from it, and then turns it into a proposition. Okay, so I've got James's proposition and I've got my proposition. I've got 2 out of 3. I need Nick's, which he sent over to me in a chat message. So proposition, going to do the same thing. Going to decode the base 58 encoded string that he sent over to me. Do that. Paste that. And there we go. Okay, so we got 3 propositions here. Remember, 3 of us own this account, but it only takes 2 of us to spend from it. Okay, so 2 of us, 3. That's called, well, it's called a threshold proposition. So you need to meet some minimum threshold of a set of propositions in order for that to be valid. You can also think of it as N of M threshold proposition. If you want to go look that up on Wikipedia for more information, it's just other terminology for it. Okay, but I'm going to take these 3 propositions and I'm going to convert them into a single threshold proposition. So threshold proposition, and this is going to be of type propositions dot compositional, because we're composing multiple propositions together, dot threshold. Okay, and this is going to be, well, to do that, there are a couple of ways to do that. I'm going to use a little helper syntax method though. So I'm going to take our, well, I guess I could just do it with a list. I'm going to take our 3 propositions. So Sean proposition, James proposition, and Nick proposition. And I'm going to do dot threshold. Hopefully it pops up. Please pop up. Please pop up. Yes. 2. Okay, so this is now a threshold proposition. So I took the 3 of our propositions and I combined them together. So that's this list here, these, this thing up here. And then I specified a minimum of 2 of us are required in order to spend from, this proposition. Okay, so we have our proposition and we can, we're on our way to being able to spend a box to pay the utility company. Okay, but what's the utility company's address? Well, luckily they sent that one over to me as well. So utility company address, and that's a spending address. And I have another little helper method, so decode spending address, and it takes in a base 58 encoded string, and I'll let you figure out what that one does. It just decodes it into a spending address. So yeah, this is what the utility company sent to me. That's their address. That's where they want you to send all the payments to for the utility. Okay, so we've got that. Now I think we are ready to actually create a transaction. So we know who is going to be sending the funds and we know who's going to be receiving the funds. So let's create a transaction to do that. But first, it's got to be an unproven transaction. So no proofs on it yet. So we're going to create an unproven transaction. This is a transaction.unproven. And an unproven transaction takes several unproven inputs. That's the main distinction between just a regular old transaction is the structure of the inputs. So this is a chain, chain from cats, basically just a list, but with other performance characteristics. So we've got a chain of inputs. So we're spending our shared box. The 3 of us, we own this box. So I need to specify the input that I'm going to spend. And this is where I want to hop in with a quick comment here from the chat. From mgrand. So the SDK will provide the account abstraction in the future. So if you remember, back at the beginning of this broadcast, I mentioned that we're a UTXO model and we don't have accounts. And that's like technically true down at the low level of the protocol. But from the user level, you could still imagine all of your funds being available in some account. They're just split across several boxes. Okay, but your account is basically just associated with your address. So your address can own several boxes on the chain, for example, or at least be associated to it. So the SDK that we provide, it's going to give you helper methods that, well, it just gives you the abstraction of an account, essentially. Gives you access to all of the available boxes that you could spend. But for now, we're just going to arbitrarily generate the box that we're going to spend. So we don't actually have, the mechanism for it quite yet to, be able to pick the box for you. So I'm just going to, use a model generator to generate one. It's not important for the moment because we're not actually going to submit this transaction anywhere. But just going to do an arbitrary box ID, the arbitrary dot first. And so this just gives us a random box that we're going to spend. It doesn't actually exist, just, pretend it does. And so that's the box ID. The second argument is the proposition associated with the address of the box that we're spending. Okay, so the box that's stamped on the chain, it doesn't actually store the proposition that can spend it. That gets revealed by like a transaction. Okay, so all that's actually stored on the history of the chain is the address associated with the proposition, but not the actual proposition. So this is where I need to go and reveal our threshold proposition. Okay, so threshold proposition that we created above. And then finally, the third parameter here is the value of the box we're spending. So box.values, and we've got 500 polys or $500 in this account. Okie dokie. Yeah, so yeah. M Grand, I'll come back to your comment in a second because I do want to make note of that in the output that I'm about to create, or the outputs, I should say. So yeah, I'll highlight that in just a second here. So outputs equals another chain. Okay, so this is where we need to actually say this money is going to the utility company. Okay, so our output, the first parameter is, well, in this case, it's a full address, not just the spending address. I went over that, in the previous broadcast. There's a, a little, distinction here. Yes, I can highlight this one. It's a little unclear. We're talking about tetra. If this were Dion territory, we would be talking about nanopolys in this case. Okay, so nanopoly, there are, Nick, correct me if I'm wrong. There's 1,000 nanopolys in a poly.
It is 10 to the 9, negative 9. So there's a million.
Million. I can't count that high.
That sounds right. Yeah.
That's a lot of zeros. Anyway, if I were actually sending, or if this box had 500 polys, then this would be more like, I can't type at all. 500 million nanopolys. There's that distinction. Ethereum has like a similar thing with, Ethereum and then Gwei and all that other stuff. So yeah, there's just like denominations of these units here. For now, because I'm bad at math, I like small numbers. I'm going to keep it at 500 instead of 500 million. Okay, so we need to send to the utility company. So I'm going to plug in utilities spending address that I defined up above. So again, this is just another little helper method that I defined in utils that just wraps this with a staking address that I own. Okay, and then if the utility company wants to move those funds to get their stake benefit out of it, then they would have to just transfer the funds to a different staking address. But not important for right now. Don't worry about that. That'll be important later. Okay. Second, I need to be defining a transaction to output. Sorry about that. Go. Okay. So yeah, that's our first argument. Second argument is the value of this output that we're creating. So box.values, and again, this is the polys versus nanopolys distinction. But for now, I'll just keep the numbers simple. And the utility company wanted, what did we say? $80 from us. So give them 80. And then the third one, don't worry about it for now. It's just minting is false. We're not dealing with assets at the moment, and we're not dealing with rewards transactions, so it's not important. Okay, so that's one output. The second output, however, we want the remaining funds to come back to us, to Nick, James, and I, so that we can spend it. We can give the utility company more money next month, because James likes to set the AC really, really low. It drives us crazy. It's like the utility bill is just sky high. It's incredible. Okay, so we need some of that money back, though. We need the change for this transaction. So we'll take the leftovers. For now, we'll just, don't worry about the fees or anything. In Tetra, the fees are implicit. If I didn't include a second output on here, then the minter would just get anything that's left over. But for now, I don't really want them to have that. So to full address. And then I'm going to triple question mark this for now, because that's where I want to come back to a comment in the chat. So this second argument is the value that we want, and of course 420 is 500 minus 80. Okay, I will come back to that comment in just a sec. Actually, I'll mention it now. Yes, so small correction, a billionth. We added way more zeros on there. That many nanopolys. Elon Musk would be so proud. So yeah, 1 billion nanopolys in a poly. So yes, thank you for the correction. Okay. So left over here is just 420. And then finally, again, just minting is false. Put a triple question mark here, and that's because I wanted to highlight this because I'm about to do something bad. Okay, so I'm going to reuse the address that we spent from originally. This is usually a bad practice because if quantum computers ever take off, then they could break the encryption on this. We've sorry, not the encryption. We've already revealed this proposition once, and because we've revealed it once, they could derive the secret keys associated with it, and then be able to hijack our account. So, in an ideal world, you do not reuse the same proposition or the same address that has already been revealed on the chain. But I'm going to do a bad thing now and just reuse the same one that James, Nick, and I already spent from originally. Okay, so this is a proposition, then it's just dot spending address. I highlighted this comment because the account will be associated with a series of single-use addresses. So yeah, you only want to use this address once on the chain, and then that verification key, or well, the secret key associated with it after you've revealed the verification key, you want to get rid of it. Maybe not get rid of it, but you don't want to use it ever again. You don't want to sign a new transaction with that same secret key, which means you don't want to create an output that goes to the same secret key either. That's just a security thing, quantum security. So yeah, it's just good practice to always use a brand new key each time, and that's where we're using ed25519 keys right now, but that's where extended ed25519 comes into play because you can just derive the next index. So if you got index 0 and that's what we started with, that's what we spent from, well, this next proposition or next address that I send to would go to index 1, and then the next one would go to index 2, and as a result, you get a new verification key. And they can't break the reversibility of it. But yeah, so for now, I'm just going to reuse it. It's a bad practice, though. Okay, so those are our two outputs. The sum total gets us back up to the 500. So 80 goes to the utility company, and then 420 goes back to the 3 roommates. All right, so final 2 arguments on here. Chronology, not too important for this use case, although, I mean, we could do something interesting where we don't want this transaction to be included halfway through the next month, because that's a problem. Utility companies can be very, very upset with us. You don't want to be late on your bill payments. But for now, we'll just use basics. Don't worry about that. What that means. And then final thing here is just a little bit of transaction data that we can associate with it. So it's just basically a string, a text string, 127 characters maximum. It's got to be Latin 1 data compatible, so each character fits within a byte, at least for now. Don't know if that's going to change in the future. There's been discussions around that. Anyway, I got another little helper method that helps take a string and just gets it into the form of transaction data, like proper sizing and all that stuff, and handles all the. It doesn't handle the errors actually. Technically, that's the problem with it. Anyway, this is like putting a subject on your check if you're writing a check. So I'm just going to say utility bill for June 30th, 2020. Yeah, goodness, 2022. And I'm just going to do that sum. Okay. I've got an unproven transaction where I'm spending from the box that the 3 of us own, and I'm using our threshold proposition. And I am moving the funds. I'm moving 80 of those polys over to the utility company, and then 420 of those polys back to us. Okay, but again, this is just unproven. We haven't actually proven this transaction yet. And that's our next step. So in order to prove a transaction, I need a credential. So I'm going to turn the secret key that I loaded from disk up here, I'm going to turn that into a credential. So Sean's credential, and it's, yeah, I won't even do that. So credential.knowledge.ed25519. And it takes 2 things here. The first one is that secret key that I just mentioned. And then the second argument is the unproven transaction that we will be signing. So this one that I just created up above, unproven transaction. And don't help me, IntelliJ. I didn't want you to. Okay, so that's just my credential though. And I guess, yeah, maybe I'll add a type annotation node. I didn't want you to do it like that. Okay. Goodness. So yeah, it's an Ed25519 credential, but I need a threshold credential. So I need to turn this Ed25519 credential into a threshold credential. So to do that, I'm going to do threshold credential is credential.compositional threshold. And now I need the proposition from up here. It's the first argument. And the second thing is just a list of like sub credentials or primitive credentials. Really, I was thinking about this earlier. I don't know if James is watching, but I think that these are like knowledge credentials. That's like these basic sets of credentials. So yeah, this is the one that I just defined, Sean credential. Okay. And now I am ready to prove my transaction. But, well, it's only going to be partially proven because I'm only putting my proof on it. I'm only putting my signature on it. We need a minimum of 2, though, so that's going to be the next step. So partially proven transaction is going to include just my proofs. This will technically be a full transaction. It just wouldn't verify to true if you sent it through a verifier. So I'm going to take my unproven transaction and I'm going to prove, and I'm going to match on just a specific threshold proposition that I defined above, and I'm going to associate that proposition with the proof from my credential. Well, not my credential, but sorry, the threshold credential, this one. Okay, so we do that. This thing is just like the starting proof, and for now it's just proofs.false. So we have a transaction. And it's partially proven. It only has 1 out of the 2 minimum signatures needed. So I'm going to print out the signature so that, well, first we can see that it actually did the thing. So your transaction is partially proven. Transaction. Oh. And next, just to kind of see what the structure of the proof is at the moment, I'm going to print out just the proof. We could see it in the print line statement that I just did up above, but it's going to be very difficult to read through it. They haven't implemented a good show method on this yet. Get to that eventually. So partially proven transaction dot inputs, and we only have one input on here, head option. Gonna do a dot get. Don't do that in your production code, please. Just doing it for now. Okay. So just printing out the proof that we have stamped on there right now. And then finally, this is the part that I need to send over to Nick because Nick is going to do part 3, which is to add his proof to this transaction. But in order to do that, he needs to get access to this transaction that I'm creating here on my computer. So I'm going to print out the bytes for that. So I'm going to send these transaction bytes to Nick to sign and broadcast. Okay, so I'm going to take the partially proven transaction mutable bytes and then back to base 58 to make it easy to copy paste, or well, to make it easy to double click, I should say. Okay, then just yield at the end. Ah, heck. What? No, I promise it exists. Missing an import. Oh, it's because I auto formatted. Silly me. It's okay. So this is codex.bytes.typeclasses.implicits._, and that should hopefully give us access to the syntax for immutable bytes. We should already have the instance. There we go. Cool. Run. How much you want to bet it's going to fail on me here? Ha, well, you would have lost that bet. Maybe. Okay, so yeah, as I mentioned, printing out the transaction, but it's a nightmare to read through, so not even going to bother. More interested here in this proof. Yeah. So this proof is a threshold proof, and it's got a list of 3 subproofs in there at the moment. Okay, so there's ed25519. That's my signature that I just put on there. Okay, so I did that. But then it filled in false and false for the other 2 proofs. So we need 2 of these things to evaluate to true, a minimum of 2. So right now, we only have 1. So I'm going to send this string over to Nick using our super secret spy chat channel. And that's going to be the immutable bytes that he's going to attach his signature to, essentially. So let me do that real quick, and I will pass this right on back over to Nick.
All right. So grab the that string representing the where did my let me share my screen again. All right, grab that super secret string. So we're going to bounce back over here. So I ran that, created the key. So now we're going to run. So this step of the process is now that Sean has sent me that transaction represented as these bytes, I'm going to decode that transaction, take the raw transaction itself, and then generate my proof and add it to the threshold proposition. So then it'll have Sean's and mine, and those together will form a valid proof that when I go to actually send this transaction and broadcast it and have it, try and be validated by a node, it'll actually work because it'll pass the 2 out of 3 minimum for this threshold proposition. So we're going to call this complete, and let's say complete and broadcast transaction. So. So we're going to set this up as another simple IO app. I'm just going to have to write everything and add our utils. All right, so the first thing we're going to need is this this partial transaction. So what we have right here is actually is this partial transaction represented as base 58. So we're just going to go ahead and pop that in. It's very long. So this is our entire transaction represented as these base 58 coded bytes. So what we actually want to do now is we're going to turn that back into the transaction. And wait a second to see if it's going to. Oh.
You may need to add extends in there as well.
That's why it's not happy with me. And then it's going to ask me to add in the run again. Whoa.
I can hear your laptop is audibly upset with you.
Yes. Okay, I was not sure if that was coming through. Yeah, I did not like that, apparently. Okay, well, we're going to go ahead and add in the run and do nothing for now. Yeah, this is taking a while to analyze everything. Luckily, I can. I've memorized everything ahead of time, so I don't have to worry about this.
Yeah, definitely. Yep.
Yeah. So we're going to take this partial transaction that's encoded in this base 58, and then we're actually going to decode it from base 58. So there we go. Now it's getting a little faster. So we're going to take that. Decode immutable. Shows up as a type transaction. And then so it's going to return either. So we're going to just do get or else. And we're just going to hope it works. So we're just going to put, I don't know what's going to happen if it fails. Okay, so this is going to decode it, turn it into a transaction. Now, this transaction still includes the proof that that Sean sent along with the transaction. So in the actual inputs, there's also going to be that that partial proof in this transaction. So what I actually want is the full unproven transaction. I guess this will take me here. So if we want to go see this really quick, okay, that works too. So what I'm talking about is in these inputs. So we have transaction as inputs, outputs, chronology, timestamp, and then data. So okay. There we go. So we have unproven right here. So we have transaction, but we also have this unproven case class. So you notice here in this transaction, it has transaction.input as the inputs. This has transaction.unproven.input. And so the difference is the input under transaction includes this proof, and while this one does not. Okay, we got 10 minutes. We can do this. So we're going to take the partially proven transaction. Yes, and then we're simply just going to get unproven. Maybe recognizes it. Okay, so that is all the things that we need so far for the transaction itself to set that up. And then what we're going to do in here now is we're going to run another for comprehension to run all the actual setup and output the completed transaction at the end. So the first thing that we're going to need to do is I'm going to need my key. So we're going to grab my secret key that was generated, which is up here. So we're going to load that key back in. And if y'all are still following at home, that was a red 25519 key, which that is not the right place to put that. So that is the type parameter for that to load this type of key in. And now we need the actual, so we need the name of this key right here, which I'm going to go back in here and grab. No. I need the address, right? So luckily that's in here, or right here. It is literally the name of the thing, which I can grab right here. There we go. Actually, I believe it should still be in here. Yep, there we go. So the Spring address was this, same as the name on here. So I can go ahead and pop that in there. All right, so that is going to load our key in. And then, let's see, I still am missing the actual password I used to encrypt that. So easy, that's just the password. So now we're going to, yeah, I can spell, threshold proposition. So now we're going to need our threshold proposition. Partially proven transaction, inputs, head option, and then we're going to get that. So we're just going to grab the first input because we know what it is, and then we're just going to get the proposition from that. So that is going to, so that's our threshold proposition. So now I need to actually cast it. We're going to have a better way of doing this in the future. For now, this is stopgap, but we are casting it as an actual threshold proposition. So we're taking that input, this generic proposition, and specifying that it is a threshold proposition. So then I'm going to actually take my credential. So what Sean had done before, from my secret key, there we go, and the unproven transaction, which is unproven transaction. So now I'm actually going to create a threshold credential from that. Threshold. We're going to take that threshold proposition that we just casted up there, and take my credential from there. So then now we're actually going to create this proven transaction. So then this proven transaction, I'm going to take the partially proven one specifically, and then I'm going to add mine to this. Case of, so let's see. Yes. We're going to take the actual threshold proposition. Wow, okay. Symbol for that. And then current proof. And then we're going to the threshold credential 50, and then we're going to prove the current proof.
And if you'll remember, I passed in proofs.false at this step, and that's because I was starting from scratch.
Right.
But Nick is starting from something that I've already given my partial proof to.
Yes. And let's see, I believe I feel like, yeah, where did this come from? Oh, that's supposed to be there. Okay. Right. So this is after. So now we're going to print out what we just did, and then add the yield there. So let's stop complaining about that. So now we're actually going to print out. So the proven transaction. So we'll see the whole transaction, and then nice. Gonna beat the clock. And then we'll add some lines here. So the actual proof is going to be this. We'll go ahead and grab it from the proven transaction because it's going to spit a lot in that first one. So we'll just go ahead and go into it, and we'll go grab it from the proven transaction. So instead of me doing this, threshold condition, since we did the threshold credential and then we did the prove, so we placed that in the transaction, so we can just go in and grab it and then print it out specifically right here. Then we'll add some more lines around that. And the last thing we're going to do is we're going to use our handy broadcast transaction utility that we're passing in here. We're going to broadcast that proven transaction. All right. So everything should be good to go. And then it's going to take 3 minutes to build, of course, and put us after 5.
SBT, the slow build tool.
Oof, okay. All right. So we can see that the proven transaction's up here, and it has all of the information that we put in. So it correctly grabbed the same transaction that's that Sean had sent me. And then this here itself is the proof. So you can see we have the threshold. So first key, false, second key. So it still has that false in there. So it still is, it is a threshold proposition. We have 2 out of 3 keys, and we're still retaining that false. So when we pass this around, it has everything it needs to verify those specific keys when it goes to prove this transaction. So yeah. And I guess that puts us right at time. And so if we had extra time, bonus points was going to be showing a similar mechanism using Gnosis Vault in Ethereum to compare and contrast of they have to set up, an entire smart contract and deploy, multiple smart contracts to achieve the same setup where we can just do this directly on chain. But yeah, so, we'll make this, we'll continue to iterate through, make this an easier process. And, the nice thing is it's all cryptography. So it all just works every single time as long as you construct it. It's all proofs. All right, cool. Indeed. Any other thoughts, Sean?
No, just the utility companies are going to get paid. We didn't need James to do it. We just needed, you and I, just the 2 of us. We can make it if we try.
Start breaking out in a song.
I don't sing well. I dance even worse.
That's okay. They can't see you on screen right now anyway, so wouldn't know if you were dancing. You could have been dancing the whole time. All right. Well, thank y'all for joining us. I hope this has been at least easy enough to follow along.
But if it wasn't, we are always open to suggestions for improvement. Definitely ask questions. Feel free to reach out. And we'll do our best to accommodate our users. That's what we're here for. That's all we're here for. See, really the only reason that we're here is to make the users as productive as possible.
Absolutely.
So yeah, thanks a bunch, Nick. This is a fun one. I guess I will go ahead with this outro thingamabob.
Sounds good.
Yeah, cool. Thanks a bunch for tuning in, everyone. That's all for today. If you have any questions or comments, feel free to leave a comment in the chat, or of course you can visit us on Discord. Happy to answer any questions there. But of course you could also follow us on Twitter, YouTube, or LinkedIn, and Twitch if you're watching there. If you're interested in the code, you can check it out on GitHub. And if you're just interested in general information about our company, you can visit us at topple.co. And just want to mention we're also hiring. So if you're looking for a new career path in the blockchain space, check us out on angel.co. Hope everyone has a great morning, day, night, wherever you're happening to be watching from. Hope you enjoy the rest of it. Thanks a bunch, everyone.
Yep. Thanks, y'all.